What if reality itself isn't smooth and continuous, but pixelated, like a cosmic screen where space and time are made of the tiniest indivisible building blocks? Today, we explore one of the boldest questions in modern physics. Is the universe pixelated? For centuries, we've imagined space and time as a smooth, infinitely divisible fabric. But many of today's leading theories in physics suggest otherwise, that space-time itself might be granular at unimaginably small scales, far below what we can measure directly. This idea isn't science fiction, it's a central problem in the quest to unify quantum mechanics and general relativity. If the universe is pixelated, what's the size of a pixel? Physicists point to the Planck length, about 10 to the minus 35 meters, as a natural candidate. Below this scale, space and time might lose their meaning altogether. To probe distances smaller than the Planck length, we'd need so much energy that we'd collapse space-time into a black hole. That makes the Planck length the resolution limit of the universe, nature's smallest pixel. One of the most rigorous approaches is loop quantum gravity. In this theory, space isn't continuous, it's woven from discrete loops, forming structures called spin networks. Just as photons are quanta of light, area and volume themselves come in tiny quanta. Each grain of space is roughly 1 Planck unit across, making space-time fundamentally pixelated. Another radical perspective is digital physics. Here, the entire universe is treated as a computational system, where every unit of space stores information like a cosmic hard drive. Edward Fredkin's concept of finite nature suggests every physical quantity from time to distance is ultimately finite and discrete. In this view, particles and fields are like programs running on the universe's operating system. Causal set theory offers a different mathematical approach. Instead of smooth space, the universe is built from discrete events connected by cause and effect. Its slogan, order plus number equals geometry, means that by counting these events and arranging them in causal order, the geometry of spacetime emerges. Perhaps the most mind-bending idea comes from the holographic principle. Gerard 't Hooft and Leonard Susskind proposed that all the information in our three-dimensional universe can be encoded on a two-dimensional surface. Juan Maldacena's ADS CFT correspondence gave this mathematical form. This means that what feels like continuous three-dimensional space might actually emerge from discrete bits of information on a lower-dimensional boundary. Black holes give us another clue. The Bekenstein-Hawking entropy formula shows that the information in a black hole scales with the area of its horizon, not its volume. This strongly suggests that spacetime itself has a granular structure, with each Planck-sized area carrying one bit of information. So far, no experiment has confirmed pixelated spacetime, but scientists are testing the idea. LIGO, the Gravitational Wave Observatory, can detect changes in distance smaller than the width of a proton. Future detectors may be able to spot tiny distortions if spacetime is granular. High-energy gamma rays from distant cosmic bursts could also reveal discreteness. If photons of different energies travel at slightly different speeds, it would break Einstein's principle of Lorentz invariance and suggest a pixelated structure. The European Space Agency's GrailQuest mission aims to test this. Even within our solar system, spacecraft like Cassini have placed strict limits on loop quantum gravity's predictions, and future missions like BepiColombo could sharpen those constraints. Pixelated spacetime theories face two big puzzles. If space is grainy, why does it look perfectly smooth at human scales? Some argue it's like how fluids feel continuous even though they're made of molecules. And if spacetime is discrete, doesn't that break relativity? A lattice might create a preferred frame of reference, but approaches like causal set theory show ways to keep relativity intact. If spacetime is pixelated, the consequences are staggering. It could solve infinities in quantum gravity. It would tie physics directly to information theory and computation, suggesting the universe itself is a quantum computer. And it would reshape our understanding of causality, entropy, and even consciousness. So, is the universe pixelated? We don't know yet. Theories like loop quantum gravity, causal sets, digital physics, and holography point toward discreteness. Black hole physics and information theory strengthen the case, and new experiments are beginning to probe the question. One day we may discover that the smooth, flowing reality we experience is just an illusion, an emergent picture from the tiniest pixels of spacetime. And if that's true, then our universe is not only physical, it's computational, woven from information itself.